3.65. In 1780, in what is now referred to as Brady's Leap, Captain Sam Brady of the U.S. Continental Army escaped certain death from his enemies by running over the edge of the cliff above Ohio's Cuyahoga River, which is confined at that spot to the gorge. He landed safely on the far side of the river. It was reported that he leapt 22 feet across while falling 20 feet. Okay, so the questions that we were asked are representing the distance jumped as L, and the vertical drop is h, as shown in the figure P3.65 over here. Derive an expression for the minimum speed v he would need to make his leap if he ran straight off the cliff. Okay, so let's go ahead and write down the equation that relates position and acceleration for free fall. So let's do y actually. Y final is equal to y initial plus the initial velocity, VIY, in the y direction, times time, plus 1/2 times the acceleration times t squared. And if you remember from the previous problem, the acceleration in this problem is the same in the y direction. It's just going to be gravity. So acceleration is equal to negative g. And so we're asked to find an expression for the initial velocity in this direction, in the x direction. So moving this way. So asked to find Vx. So we're going to use the same exact approach that we used for the last problem, except we're just going to do it in terms of variables. So for this one, we know that the final position is going to be 0, right? Because it's going from here down to here. So 0 is equal to the initial position, yi, so wherever you're starting from, so we need to keep that around, yi, plus the initial velocity in the y direction. If it's free fall, it's going to be 0, so this term goes away. And the acceleration is just going to be negative g, so this just becomes negative 1/2 gt squared. Okay, now we just want to solve for t, because we want to find out the time it took him to get from the top to the bottom, so that way we can plug it in to find the initial velocity that he left the cliff with. So let's just go ahead and rearrange this equation and solve for t. So subtract yi from both sides. So negative yi is going to be equal to negative 1/2 gt squared. These negatives go away. Then we're going to multiply 2 to both sides. So we get 2yi is going to be equal to gt squared, but I'm just going to divide through by g just to make my steps a little easier. So this is equal to t squared. And so this means that t is going to be equal to 2yi over g and the square root of that. But we're asked to represent distance jumped as L and the vertical drop as h, as shown in figure 3.65. So we're asked to represent it in terms of h and L. So this yi over here, this initial position, yi, is just going to be changed to h, right? Because so we're saying that yi is going to be the same as h in this problem. So now that we have the time, we can use this exact same equation to find the initial velocity that he jumped off the cliff with. So xf, right, so now we're in the x direction, is equal to xi plus vix times time plus 1/2 at squared. But we're in the x direction now, so we're not going to have any acceleration, so this term's going to go out. We're taking this part right here, to be our 0, so the initial, so this just becomes 0, so this goes away. And so we're just left with xf is equal to vix times t. And so we're trying to solve for vix, the initial velocity, in the x direction. So now we just rearrange this equation and we get vix is equal to xf over t. But again, we're asked for it in terms of L and H, so we know that the xf, the final position, is going to be the same thing as L. So we'll just represent this as L. Okay, so now we have everything. We have t in terms of H, and we have this velocity in terms of L. So now we're just plugging in for t, because we have this right here. So now we're just going to take this, and we're going to plug it in this t right here. And so we know that Vix is going to be equal to L over the square root, so all I'm doing is plugging in, 2H over G. Now just to make this a little cleaner, I'm just going to write this as Vix is equal to L times the square root of G over 2H. Okay. So now just to put it over in metric, we know that 22 feet, I'll write this up here, 22 feet is equal to 6.71 meters, 6.71 meters. And we know that 20 feet is going to be equal to 6.10 meters. Okay, so now we have everything over here. We have, we know L, we know H, and we know G. So we're going to need that for part B, for evaluate your expression with a 22-foot jump with a 20-foot drop to the other side. So we know that L is going to be 6.71 meters. And we know that H is going to be 6.10 meters. 6.10 meters. Okay, so let's just plug in right now and see what we get. So Vix is equal to L, which is 6.71 meters, 6.71 meters, times the square root of G, which is 9.8 meters per second squared, over 2H, which is 2 times 6.1 meters. And when you put this all in your calculator, you get 6 meters per second. Okay, so that's part B. Let me circle that. So that's part B, and now let's go to part C. Is it reasonable that a person could make this leap? Use the fact that the world record for the 100-meter dash is approximately 10 seconds to estimate the maximum speed such a runner would have. So we're given a distance and a time, so all we have to do is just do velocity is equal to distance over time. So velocity is going to be equal to the distance, which is 100 meters, over time, which is 10 seconds. And so this is going to come out to 10 meters per second. So 10 meters per second is going to be the world record pace. So he clearly ran slower than the world record pace, but he's still able to make it over the gorge at 6 meters per second. So it is reasonable that a person can make the leap. And that's it for this problem.